Westerly wind shifts raise southern storm risks. New evidence reveals that even small shifts in southern hemisphere westerly winds can rapidly reorganize storm systems, precipitation, and climate risk across mid-latitude regions. By reconstructing more than 200 radiocarbon-dated peatland initiation records from South America, the Falkland Islands, Tasmania, New Zealand, and subantarctic islands, scientists show that when the southern westerly winds, SWW, migrated north or south during the last deglaciation, the hydrological impacts were immediate and hemispheric in scale. What the research shows: the analysis traces distinct phases of peatland development between 20,000 and 8,000 years ago that align with major atmospheric reorganizations. During the Antarctic cold reversal, roughly 14,700 to 12,800 years ago, the winds shifted several degrees toward the equator, moving storm systems, moisture delivery, and cold maritime air masses with them. Peat formation abruptly declined in the far south, while expanding significantly farther north, indicating an altered distribution of rainfall, storm intensity, and temperature. These patterns offer a critical warning for today. Satellite observations and reanalysis data sets show that since the mid-20th century, the SWW have strengthened and migrated poleward, producing a trend considered anomalous over the past millennium. The European Center for Medium-Range Weather Forecast's ERA5 dataset, for instance, shows consistent increases in westerly wind stress south of 50° S since the 1970s. Climate models project that this poleward shift will persist through 2100, especially under high-emission scenarios. What does all of this mean for future storms? If past behavior is a guide, modern wind intensification could reshape storm tracks across multiple regions. Windward coasts in southern Chile, Tierra del Fuego, Tasmania, and the South Island of New Zealand may see higher storm frequency and more extreme rainfall events, while leeward areas, shielded by large mountain ranges, could experience drier conditions, amplified evaporation, and broader hydrological stress. Studies from the World Meteorological Organization and NIWA, New Zealand, already report increasing rainfall extremes in westerly exposed zones and more persistent drought risks east of major topographic barriers. The research also underscores how wind-driven changes reverberate through the climate system. Stronger SWW promotes upwelling in the Southern Ocean, which can release deep, carbon-rich waters to the surface. This mechanism played a role during past rises in atmospheric CO2, an important context as scientists now observe similar upwelling intensification. A 2015 study in Science showed that the Southern Ocean carbon sink briefly weakened in the early 2000s before recovering, largely due to wind shifts. The new Nature Geoscience findings reinforce that this sensitivity is not new. It is a recurring feature of the climate system. Businesses and governments take notice. For businesses and governments, these insights carry direct implications. Water-dependent industries in Patagonia and Australia face rising uncertainty in precipitation and snowmelt patterns. Infrastructure planners must prepare for both heavier coastal storms and more persistent inland drought. Energy developers, particularly hydropower operators, may need to account for nonlinear changes in regional runoff. And climate risk disclosures under ISSB and TCFD frameworks increasingly require such region-specific analyses. The study demonstrates that climate thresholds associated with westerlies can shift rapidly and with far-reaching impact. As anthropogenic warming accelerates these atmospheric changes, understanding storm belt migration is becoming central to forecasting extreme weather risk, long-term hydrological stability, and carbon cycle behavior across the Southern Hemisphere. You've been listening to Sustainability Soundbites presented by E+E Leader. For partnership opportunities, reach out to a member of our team.